As the body moves under the action of one or several forces, we may many a times want to analyze how much energy each of the forces has pumped into the system. So we define a physical quantity called as work. The definition involves calculus. So work done by a force is given as integration of the dot product of the force with the small displacement ds from point A to point B on a given path. So this is work done by the force F. So let us say this is the path of the body. What we do is we divide the path into small, infinitesimally small in fact, displacements. Each displacement is noted as ds. Let us say the force at this point was as shown. Then the angle between the force and the displacement at this point happens to be theta, and momentarily the magnitude of the force is F. So momentarily this will result into F cos theta ds. Why cos theta? Because we are taking the dot product, and since we have already taken the magnitude of the dot product, I don't need to write the vector symbol on top of F and ds. So this is what we are integrating from point A to point B in the path. Many a times what happens is the force F is given to be constant in magnitude. In such a case, whenever the force F is constant in magnitude, the magnitude of force F will be taken out of the integral sign and will be left with ds cos theta only. In many cases, the force F is also constant in magnitude as well as direction. In such a case, F cos theta can be taken outside the integral sign and will be left with integration of ds only. So this is assuming that the angle theta is also constant between ds and F. So this results in the following. Whenever there is a constant force given, what we end up doing is work done by that force is equal to integration of F dot ds. Yes. However, since the force is constant, this also results into the equation F dot integration of ds because the force is constant. So this results in F dot delta S bar, where delta S bar is the total change in displacement. So let us say this is the path that we have. So small ds are vectors that go from point A to point B. Now according to the polygon law of vector addition, as the small ds vectors are so written, the resultant is going to be the vector that joins the head of the final vector and starts from the tail of the initial vector. So this is the total displacement, which is essentially the shortest straight line distance between the initial and the final point. So this is the work done expression that we use for a constant force, a force that is constant in magnitude as well as direction. Sometimes a force may be constant only in magnitude but not in direction. In that case, we may need to integrate. If that happens, then we may need to integrate F integration of cos theta ds. In such a case, the result may depend upon the problem. Next is when we have a variable force. So whenever we do have a variable force, we may need to keep the force F inside the integral sign and find out the work done on a case to case basis according to the problem. So one example we'll see over here of such a force is, let's say the force is given to be F bar is equal to 2x I cap plus y j cap. So this is a variable force. It depends upon the x coordinate as is seen over here. So let us say these are the two axes. This is the y-axis and this is the x-axis. So let us say the particle moves from point A to point B. The coordinates of point B are b comma 0. A is at the origin, so its coordinates are 0 comma 0. And then the particle moved from point B to point C. The coordinates of point C are b comma k, let's say. So k is the y coordinate and here b is this distance AB. Okay. So if we were to find out the work done by this force in taking the particle from A to C, then we'll have to go according to the path that the particle followed. So basically we'll have to find work done from A to C is equal to integration of f dot ds. It first went from A to B plus, according to the rules of definite integration, then it went from B to C, integration of f dot ds. Now the most important thing to understand is that the position vector in such a case is given as r bar is equal to x I cap plus y j cap. So ds, the displacement vector, is simply equal to the change in position vector is simply equal to dx I cap plus dy j cap. So when we do f dot ds, we get work done on path AB to be equal to, so for path AB the y coordinate is 0, so the force boils down to 2x I cap. You need to take dot product with dx I cap plus dy j cap. So this is from point A to point B. So point A can be written as 0 comma 0 and point B can be written as b comma 0 as the limits of integration. So this comes out to be 2x dx. So y is not varying, so we don't bother about y coordinate over here. If it was varying, then we would have bothered, and x is varying from 0 to b. So this is going to be 2x square divided by 2. So answer is going to be x square, and that x square is going from 0 to b. So the answer is going to be b square. So the work done in path AB happens to be b square. By similar logic, the work done in path BC, so the work done in path BC will depend only upon the y coordinate. Why? Because dx happens to be 0. Dx happens to be 0. So let me write down the entire expression. So from B to C, the force is 2x I cap plus y j cap. So there is an x component of force, unlike path AB where there was no y component of force. So here there is an x component of force. However, the displacement is 0 in the x direction. So dot dx I cap plus dy j cap. So by observation we can see that as it vertically moves up from point B to point C, then the dx displacement happens to be 0. So here, as we take the dot product, there is not going to be any x variable, only y variable is going to be there. So we get integration. Again, since there is not going to be any x variable, I'll much rather bother only about the y variable, 0 to k, integration of 0 to k by dy. Yeah, j cap dot j cap happens to be 1. So the answer over here is y square by 2 from 0 to k. So the ultimate answer for work BC is k square over 2. This is the work done for the path BC. So the net work, we can now understand that the net work is going to be equal to work done for the path AB plus work done for the path BC. So it's going to be equal to B square plus k square by 2. So many a times, in order to find the work done, so this is just an example, many a times in order to find the work done for variable forces, we may need to perform operations of integration over various paths.